Thanks, Denton. Good evening, everyone, Engineers Australia members and guests. It's a great privilege to have the opportunity to speak to you all tonight. And as the title suggests, our team's very keen to look at how we can maximise ADF personnel performance in austere environments. You'll probably gather that I'm not an engineer. I'm a human scientist. But tonight what I'm going to do is have the opportunity to talk to you about the complexity of the human system and how we can use human-centred design approaches to maximise the fit for purpose and capabilities of engineered systems. I'll concentrate on two topics. One's more the heat injury management and the other's our role with Army and Digger Works in developing and continuing to develop the body armour systems. I thought before I start, I'd like to actually acknowledge the huge number of people that have been involved in most of this work. What I've listed there are the people from DST. I haven't listed our partners. There'd be at least another 30 names up there, but due to the breadth of work that we do, there's lots of different disciplines from the human science. Plus, when we're doing human science, we tend to have lots of people in the field collecting the data. But the way we're looking and continue to look to operate is that we look to broaden and deepen our S&T expertise and capabilities with partnering with key universities. We look to partner with industry to transition capabilities that we're working with into the hands of warfighters. And you'll see there that there's three organisations at the bottom of the screen where we heavily work with our international partners to rapidly get insights and transition that into the Australian defence environment, but also we are continuing to share the burden of research across the nations. I thought I'd start with a little bit of a background of how examples of how heat injuries can really impact on the capability of defence. It was in World War I in the Middle East that the British Army suffered over 600 deaths from heat injuries. Interestingly, in World War II, the US had around 250 deaths on US soil while training from heat injuries. But probably the biggest event happened in the Six-Day War between Israel and Egypt in 1967, where the intelligence reports found that there was 20,000 dead Egyptian soldiers in the desert with no visible trauma, and they suspected it was heat stroke and or dehydration. So that's the effect on deaths, and that's pretty catastrophic. But it's not just deaths. These pictures here that we've got here I've got up on the screen at the moment are representing what happens in a jungle warfare environment. So in 1996, I'm talking another little anecdote here. In 1996, US Army were conducting a training activity in Puerto Rico. And what they were looking at doing is have an infantry platoon, so around 40 soldiers were going to do a surprise attack on a guerrilla camp in the jungle. Now, even at night it was hot there. And so what they did was they got their fittest, most acclimatised platoon. They made sure that they had lead-up training, they were fully rested, they were fully hydrated, and they set off to do this surprise attack. But they had to cut their way through the jungle. And so they started off, Private Smith was macheting his way through the jungle, leading the platoon, and the squad leader decided to give him a rest because he realised how physically demanding and how hard it was. So Private Jones went up the front and he started cutting his way through, but he wasn't actually going fast enough, and Private Smith kept on hassling his squadron leader to take over the duties. The squadron leader refused on a number of occasions, but then eventually gave in and let him take over. It was probably within 10 minutes he was on the ground, incapacitated, and they had to actually evacuate him out of that area. And by doing that, they had to put one person on to cutting to the left of where they were going, close to a road where they could get ambulance to him, but then they had to have 4 stretcher bearers. So 5 men had to be taken out to evacuate him. As they're evacuating him, one of the stretcher bearers goes down. So they've got to put another 5 men on to look after these 2 soldiers with one very small but poor decision. And what ended up happening is the platoon commander called off the exercise because basically they've lost one section, they've lost a quarter of their platoon. They wouldn't be able to actually continue on and complete the mission. So that's the effect it can have on defence capability. What I wanted to do on this slide was just touch on the biophysics of heat exchange and how that can impact on heat, on the human physiology. So right at the moment we're at about 37 degrees. And our operating window is only around about 36 to 39, so it's quite narrow. Once we get above 40, we can potentially start to get tissue damage, and we don't really want to go there. But with us sitting here at 37 degrees, we're actually producing 100 watts of heat. So if you remember the old light globes, 100 watts, so we're producing that much heat right now. And we're getting rid of that 100 watts of heat because we're staying at 37 degrees. So we're balancing our heat production and our heat loss. If we were to grab a soldier and throw 35 kilos on his back and get him to walk at 5 kilometres an hour, he's going to be producing 600 watts of heat. So I've got to get rid of another 500 watts. If we went into an environment where the ambient conditions are the same as our skin, so around about 33 to 35 degrees, if we're in that environment and we're wanting to get rid of 500 watts of heat, we can't use convection, we can't use conduction, we can't use radiation, we can only use evaporation. So evaporating sweat is very powerful. What would we have to do to get rid of that 500 watts? We have to evaporate around 700 mils of sweat an hour, so a Coke bottle an hour, to actually make sure we can get rid of that 500 watts. But the thing is that when we do sweat, a lot drops on the floor, so that's not evaporating, so we're not losing as much heat. It goes into our shirts and so on. We probably need to sweat a litre to evaporate 700 mils. So here we are, we're sweating a litre an hour just to get rid of that heat. What does that do? We start to lose blood volume. So at the moment we need to have blood going to the brain to supply oxygen and nutrients, but when we're working we need it to go to the muscle, and if it's hot we need it to go to our skin because our skin's our radiator. So we've got these 3 competing demands for where the blood's going, but our blood volume's going down. So if it goes down far enough and we can't keep the blood flow to the brain does a pretty neat thing. It just says get horizontal. That stops the blood going to the muscle. It makes sure that you don't have to worry about gravity and you become, as we would say, heat exhausted. You're not going to die, but your cardiovascular system, your heart, is just not able to cope. You fall over, you're incapacitated, which is probably what happened to Private Smith. But the thing is that if our fitness levels are high enough and our motivation's high enough, we can keep on pushing, and that's when we get too hot. That's when we get to temperatures where cells start to explode, tissue starts to get damaged, organs can fail, and death can happen. So the person that doesn't have that great cardiovascular capacity is probably going to survive, and those that are fitter are going to be at much greater risk of serious injury or death. So after the tragic death of Trooper Lawrence in Mount Bundy in 2004, the ADF looked to revise its policy and guidance of how to manage work in the heat. I'm not expecting you to read all the numbers on this table, but this is the work tables that we worked on. We took most of this comes from models and mathematical equations from the US Army, where they've actually collected data for decades after World War II to model the effects of the environmental conditions, the clothing that people are going to wear, so that's all on the left-hand side here, the environmental conditions, what clothing they've got on. So that tells us how much heat can be lost. Then we've got heat production. How heavy are we working? So there's our production and here's our loss. When we balance it up, we can figure out how long someone can work for. So they're the 3 key factors that we need when we're trying to risk manage or predict the achievability of an activity. So here's a scenario. We've got a guy with 30 kilos on, he's walking at 4 kilometres an hour. He's doing moderate work. Let's say he was in Darwin, mid-morning in summer. I'll go into WBGT in a minute, but the main point, it's 31 degrees WBGT. He's just wearing his camouflage uniform, DPCU. He's only going to be able to go for 80 minutes. So if he's walking at 4 kilometres an hour, he's not going to go much more than 6 kilometres. So how can we actually get him to go further? we can wait till it's night time. So in Darwin, overnight, it'll drop to around 26 degrees WBGT. Then you can go no limit, which is around 5 hours. So we'll be able to actually get 20 kilometres out. Or alternatively, if we actually throw the pack off, or most of the weight, or we reduce our speed down to around 2.5 kilometres an hour, we'll go to light work and we'll actually be able to work much longer. And obviously, going for 5 hours at 2.5 kilometres an hour is a lot greater distance than actually at 4 kilometres an hour. So this is how we can use those mathematical models from the human data to risk manage activities. But one of the challenges that Army had was it can easily, not easily, but it can predict what the work intensities are. It knows what we're wearing, but how does it go about measuring the environmental conditions? So wet bulb globe temperature is a measure that came about after World War II with US Marines. And it's this monitor here on the left. It's got a black globe here that's looking at solar radiation, a wet bulb for humidity, and a dry bulb. So it simply brings those numbers together and gives a single number that is the aim is for it to be independent of whether it's 40 degrees and 2% humidity or 30 degrees and 80% humidity. Doesn't matter, the WBGT will be the same and the work intensity will be the same. I'm not going to go into the science behind that, but what happened after Lawrence's death is that Defence went out and bought hundreds of these. They're around about $3,500 each, yet they're very simple tools. What we were looking at the same time was US Army again had been looking at using micro sensors, so using a very small temperature humidity sensor and a light sensor to actually predict WBGT, and that's the monitor you see there. But what the US were trying to do, they were trying to put it into a watch. Problem is in a watch there's all sorts of micro environments going on. It really didn't work. So what we did, we put it into a much larger handheld device. We worked with Ideation Product Solutions in Melbourne, and we patented and commercialised it. Now Army have 2,500 of those monitors to be able to more easily manage what's happening in that particular environment, because the activity might be across a 50 by 50 kilometre square grid, and with one WBGT at one location, it's not telling you exactly what the conditions are everywhere. So it's actually quite a novel little monitor as well, where instead of calibrating it each year, you simply unscrew the sensors at the bottom, throw them away and put another lot in, because it's actually cheaper to replace the sensors than to calibrate it in relation to labour costs and so on. And here's just some data over a 48-hour period in Darwin. You can see that that we're going through the night into the day, through the night and into the day. The temperature in WBGT is going from around 24 up to 34, and you can see that the ESI and the WBGT match quite closely. One of the things that we have done though is that the equation that was published by US Army, we've tweaked it a little bit, because the solar radiation in Australia we found was a little bit more intense than in the northern hemisphere, and so we've got actually a proprietary equation in there that estimates it in Australian conditions. So I've talked about how we can manage heat stress using the tables. I've talked about how we can monitor the environment. But the big challenge we have with humans is that they're not like a tank. They're not going to heat up exactly the same amount each day, and each tank is going to be doing the same thing. And we know from an engineering perspective that they will operate in a certain window. What we actually understand is humans are quite varied in what they're going to do in relation to their core temperature elevation. And the tables that I showed you before are based on an average soldier. So the model's based on a person starting at 37 degrees, as we are sitting here at the moment, and going up to 38.5 degrees. Now 38.5 degrees isn't a really high body core temperature. But the thing is that we know that probably around 5 to 10% will be above 39. That's just due to the human variation we have in a ready population of a platoon or a brigade ready to be deployed. So, but if we're going to have some people at 39, we're going to have some people below 38 that aren't really that strained at all. And that's the real challenge that Defence has, is how do we continue to provide a sufficient enough stimulus, training stimulus to those that aren't going to be as stressed. And what we've done I'll talk about a little bit later, but we've been involved with setting the physical employment standards for Army as well. And one of those tests was a 10K march, which takes 2 hours to do, carrying 35, 40, 50 kilos, which ends up being a heavy work activity. And if we're going for 2 hours, we can only do it in a WBGT below 22. And I'm not sure if you saw before, but in Darwin, in summer, it doesn't go below 26. So for about 5 months of the year, we can't do physical employment standards in Darwin. So what we did was we've done a few little studies where we've looked at how confident are we with the tables? How far can we push it? So if we want to do a two-hour march, can we go up to 24? At the moment, it's only saying 75 minutes. Really, we've got to go below 22 if we want to be able to achieve it. So what we did was, and this is the great thing of humans, we got them to, again, a platoon of soldiers ready to deploy and got them to do the physical employment assessment of the 10K march. And this is what we got. This is how much variability we've got in that particular section. So a couple of points to note is at the start of the march is around about a degree difference. Once we get out to 60 minutes, we've got about 2.5 degree difference. So we can see that our 38.5, we've got a lot of people up around there and a lot of people below it. You can see that these guys can easily do it in a WBGT of 24 degrees. They can do 2 hours. And what we're seeing here is that we'd call this a compensable environment. So core temperature goes up and then plateaus because we're balancing heat loss and heat gain or heat production. So 2/3 of the soldiers are fine. They can work well beyond the tables. The people we've got problems with are these guys here where look how quick their core temperature's actually gone up. So this was the hypothermic group where we had to stop them. And they actually probably needed to be stopped slightly before the tables would recommend. They're our real risk group that could suffer from heat stroke and organ damage. We've got our symptomatic group that found in orange, and they were finding it quite tough. Their heart rates were high, they were feeling dizzy. They either stopped themselves or we stopped them because they couldn't even walk straight. But you can see that the hard thing with those guys is that their core temperatures aren't all that high, but they're going to fall over from heat exhaustion. So this shows the human variability we have and the difficulty of providing guidance that in some ways is really protecting the minority to some degree, and that's great from health and safety, but the thing is we're losing potential ability to actually further condition the guys that could go longer. So what we did was we know that things like body fat, cardiovascular fitness and other things, physiological parameters affect people's tolerance to heat or the rate at which core temperature goes up, because adipose tissue compared to muscular tissue will heat up about 50% quicker. But when we looked at all these subjects, we could not pick those ones in red. We can't pick who they are. We can't figure out who they're going to be. And I think that's where a lot of the science is really interested in. How can we predict these people so we can put them into different trades where they're not going to be a potential injury, but it also lets the more capable people get on and be pushed further. The only thing that, the other thing, and we've been working a little bit with some of our Air Force colleagues in theatre at the moment as well, is when we want to push beyond the tables, what can we do? Well, we can go to individual monitoring. So if we monitor people and we monitor their core temperature, then we don't have to worry about the tables. We can just risk manage on that individual case. This is a slide that's come from US Army a few years ago, and this is the human dashboard. We know that wearables are around. Most people are wearing them at the moment, and sensors are getting lighter, and we're able to measure more things. But the real problem is who is actually looking at this data? What decisions are they making? How could a corporal make a decision on whether that soldier should stop? There is too much information there. So while we're getting all this extra information coming out, we need to make it so it's simple to use. And what we're looking at with our US Army colleagues is to provide them the data that we collect from the field and what they collect from the field. What they're looking at is looking to model, to mathematically predict when someone's going to fall over. So if we know what their body temperatures, so if we look at skin temperature and heart rate, if we can measure that now and they continue to work at the same rate, where will they be in 20 minutes? And because in 20 minutes time you can do something about it, but if it's an alarm to go, this person's about to fall over, it's too late. You can't really do anything. You can't replan or change the way the operation's happening. So the focus at the moment is looking at how we can predict where a soldier's going to be not too far into the future. All right, so I'm going to change tack now. So I've talked a lot about heat injury management and how we can use sensors and how we've been measuring the environment and so on. I'll go a little bit more into sort of like how we can work more a bit with engineers in relation to body armour and what we've been doing with DiggerWorks. So DiggerWorks is really Army's responsible for understanding how we can extract the most out of our soldier combat system. And what I'd first do is just to make sure, some people may be familiar with body armour, others mightn't. What I've got here is a picture of the body armour system. So what it's composed of is two bits at the moment. The first bit is the hard ballistic plate on the front. And so that's a composite with a ceramic strike face. The ceramic is usually boron or silicon carbide, and that's as far as I'm going to talk about materials and so on. But what that's there for is to stop 7.62 rounds coming from an AK-47 that you see on the left, or a 5.56 round, which is what comes from most NATO standard rifles. And the 7.62, it's going to be travelling at around about 800 metres per second, whereas your 5.56 is going to be going about 950 metres per second. So quite a lot of punch when it's going to hit, and you get quite a lot of backface deformation. What we've got behind that plate is soft armour. Usually it's an aramid or a Kevlar, and there's usually around about 30 to 33 layers behind there. That can actually stop a handgun. That's what you see most law enforcement, civil law enforcement's using, because it's going to stop a handgun. Sorry, at the bottom here I've got the 7.62 round, the 5.56 and 9mm round. The 9mm, it's about the same mass. It's not that much lighter, the actual projectile, but it's only going to be going at 400 metres per second, so half the speed. So that soft armour will stop a 9mm, but the soft armour won't stop a 7.62 or 5.56 round. So I thought I'd talk about that first, just to put in context what I'm talking about when I'm talking about body armour. What we've looked at is, and over the next 5 or 6 slides, I'll talk about the human considerations for heat strain, because essentially we're wrapping a plastic bag around our radiator, and that wouldn't be good if it was our car. Our car would start to overheat. We'll talk about mobility. So the ability for a soldier to move from point to point cover. So we've got all this extra mass, how much quicker or slower are they going to be? What organs are we covering? What organs do we need to cover? Have we got a good understanding of the size of the plate, which leads to, if we make the plate too long or too wide, is that going to actually impact on their ability to do their tasks? And then the last slide, I'll talk about curvature. We've now got ceramics that can be manufactured in a far better way, such that we can get more curvatures in, so it can hug the body better. But before I talk about that, I will just touch on the physical employment standards. And the reason I am is because we use a lot of these tests when we're assessing body armour. And so this is what the ADF physical employment standards are essentially occupational fitness tests, let's say. And what we've done is we're finishing off Navy and Air Force, but we did Army a little while ago. We went across 465 tasks across 100 different employment categories. And we've come up with these 4 tests. We've got a muscular strength task, muscular endurance, and while this is jerry carry, it's actually representing a stretcher carry, like we're talking about when they were evacuating Private Smith. This here is an anaerobic task, which is representing a section attack. And then we've got a prolonged march, which is more of an aerobic task. What we actually found was half of the tasks that Army do are actually muscular strength tasks. Yet our tests at the moment are push-ups, sit-ups and 2.4K run. So what we're hoping with the outcome of, and what has been happening, is we're looking at not only do they have to pass these tests, but then you're training the musculoskeletal systems, energy systems to actually do the military tasks required. But I will concentrate on the section attack and the march is what we'll be looking at next in relation to the body armour studies. So this is a lab study that we did a few years ago in relation to tier body armour systems. So the photos across the top, there's no armour here. This is just a chest rig where they've got their ammunition, their grenades and other sorts of items that's carried on the chest. This was called tier 1. It's just a plate on the front. There's no protection at the back. This is tier 2. This is just a plate carrier. So you can see the red is the hard plate and the blue is the soft armour. And so that's mainly just for, so these are mainly just for rifle rounds. We're not worried about fragment protection or 9mm protection. But when we get up to tier 3, and this was the old McBass, we can see that there's far more soft armour. In McBass, soft armour all through the shoulder, it goes down longer on the torso, and it's actually wider on the sides. But what we did was, in the climate chamber, we represented an Afghanistan environment, 45 degrees, 20% humidity with some sun. We did a 90-minute patrol, and then we did a 30-minute section attack. Now, we had civilians do this. The heat production was the same as what we would do in a patrol and a section attack. And so what happened? From a thermal strain perspective, adding the protection didn't actually do anything to the core temperature response between these three conditions, which was a little bit surprising, but actually quite good for something like the plate carrier. But one thing that the human is really useful at doing is that while we had the plate carrier on the front and it did reduce evaporation around there, we just sweated more on other regions. We shunted more blood flow out. So we did have greater strain. So we had higher heart rates and so on, but our core temperature and the risk of heat stroke was no greater. These two, where we've got lots of soft armour protection, yeah, they did actually impact and had about 0.5 degree effect on core and probably around about a 30% reduction in work capacity. So that was a bit of an effect there. The main thing, I suppose, with body armour is that what we're finding is that the heart rate will be affected far more than the core temperature. As I said before, more sweating, more skin blood flow going on. The body's rectifying the system to make sure that it stays in thermal balance. And we'll end up, when we model it out, we'll end up getting to a critical heart rate before we get to a critical core temperature. So we will get probably heat exhaustion. Now what we did was we went into Tully up in Northern Australia and conducted field activities with this tier 2 on, and we actually did a belt rig, because once guys are actually in a jungle environment, they're going to actually wear their webbing around their waist, not on their chest, as they would in vehicles in the more urban environment. And what we found was there was no difference in core temperatures. Obviously the soldiers felt a lot hotter with the body armour on, and that's not surprising, because the thing that tells us we're hot is our skin. If we walk into a hot room, it's not our core temperature that tells us it's hot, it's the skin. So as soon as we walk in, we've developed those sorts of mechanisms so we can behaviourally get ourselves away from hot and cold environments. So there's no doubt that people will feel worse wearing body armour, but there was no greater risk of heat stroke. So that's the heat side of things, but what about when we're adding all this extra mass onto people and they're having to actually bound between points of cover? So from our and here's the Catapult System from the company in Melbourne, which you see mostly they're putting in the footy players and so on. So it's got a 10 hertz GPS with a whole bunch of accelerometers and so on. So we've worked with Catapult and they've come up with a whole lot of data analytics so that we could actually quickly understand how far people were bounding, how long they were providing cover and so on. But what we ended up doing, we did 16 6-metre bounds and we had loads from 15 to 30 kilos. The bottom line is every kilo we add, we slow them down by about 1%. But one of the really interesting things come out here, again, human variability, is that we did it across a platoon of soldiers. What we found was the guy carrying 15 kilos, our slowest guy carrying 15 kilos, was no faster than the fastest guy carrying 30. So we had a guy carrying 30 kilos that maybe did it in 3 seconds, and we had a guy carrying 15 kilos that did it in 3 seconds. So this is a group of soldiers that are ready to go out together in war, and this guy can carry 15 kilos and move just as quick as the other guy only carrying the extra 15 kilos. So the importance of physical conditioning and being able to buffer that load is one thing that we're working on and looking at physical conditioning studies on that particular situation. But sometimes the difference we're finding here with the 1 kilo and 1%, between the 15 and 30 kilos, the difference between potentially suffering 3 shots versus 5 shots. So 2 extra shots. So the next point that we've been working on as well is understanding how much variation and what size our organs actually are. And what we've got here on the left is an MRI image, and we've done that in around 23 people. And then we've marked out some critical locations. So the circles represent the aorta, so that's the major artery coming out of the heart. The squares are representing lateral borders of the heart. The diamonds are the spleen, and the triangles are the liver. You can see how much variation we've got there. You can see we've got 2 exemplar plates here, so they're just notional plates that we've got. But you can see if you go with the smaller plate, you're not actually going to cover all of the heart in all of the soldiers. The other interesting thing is that while we're covering the top of the aorta, if you get a shot in the aorta, you're probably gone in about 5 or 10 minutes. But if soldiers aren't wearing it correctly, if it's only 5 centimetres down from where it's supposed to be, the whole aorta is actually exposed. So we thought, prior to doing this, we watched the CSI shows and they go, the bullet came through here, it hit this rib and went off to there and all this sort of stuff. We thought, great, we'll get those software. Oh no, they don't exist. So, and the medical industry, the medical fraternity are interested in mapping stuff in relation to disease states and looking at treatments and so on, but no one's really been doing what we've been doing here. So we're looking at taking that to the next step to do probably 100 to 1,000 soldiers. But the really interesting thing is it depends on when you take the scan. So we're breathing in and breathing out. The lateral border of the heart can change by 2 centimetres from breathing in and breathing out. And same with laying down or standing up. And most of the MRIs are all laying down. So we went to Sydney and did some standing up. But that's some of the challenges we've got, and just to show the variability. So we can talk about what we want to cover, but then the next point is, well, what can the soldiers actually do? So what we've got here is we've manufactured a whole bunch of different size plates, wide plates, narrow plates, long plates, short plates. And we've worked with our partners in Canada in DRDC, and so they've actually done the breadth study, and we've done the length study. We've done trials looking at a person's ability to shoot in all different postures, getting in and out. This is like a vehicle representation, and then going over obstacles and so on. And what we're looking at doing is figuring out when is the critical point that they're not going to actually start to be able to do their task. So we can really start to trade off the mobility protection argument. And lastly, what we've been looking at is the curvature. So as I said before, we know that that there's engineering techniques and materials now that can actually allow greater curvatures on plates. So what we did was we've gone around and scanned and measured around 2,500 soldiers for a new vehicle study to understand who's going to fit into vehicles. But what we did with those scans, we gave it to our mathematicians, and they came up and they worked through all of the scans and came up with some representative shapes. So this is a female shape and a male shape. We then 3D printed those and then ran a trial. And what we did was we had the SAPI plate, which is the US plate, which really just has one curve in it. So it goes like that. We had our CIB plates that we use in Australia that have a little bit more curve, and then we use this curved shape that's going to match with what the population looks like. So we got soldiers to do a number of obstacle courses and so on. We did timings, and obviously we couldn't find anything because we're only doing subtle differences here. But when we asked them about what their perception was, were they getting sore points, how did it fit and so on, they could not tell the difference between any of the plates. The really shaped ones, they did not know that that was a really highly shaped plate. And really probably the reason is we've got 33 layers of Kevlar between the plate and the body. And that just acts as really a buffer. So, and this is where what we see and from our human science perspective is armies saying, I want to go out and buy this perfectly curved plate that's awesome, that's going to cost 3 times the amount that the plates we are buying at the moment. Our suggestion would be, you're not going to get a capability advantage out of that, just keep with the ones you've got. But if we start to go into, if the system starts to change and we take away those 33 layers of Kevlar, then we might see some differences happening. So we've got to keep an open mind of how some of these material changes may actually have some benefits for soldiers. And I'll just touch on one more point on that, is that a lot of people are talking about more flexible aramids, so making the soft armour more flexible and pliable. And while that'll be great because it'll hug the skin a lot better, it may lay more torsion and flexion of the torso, but what we already know when we've trialled some of those systems is that because it actually now hugs the surface better, because the more rigid aramid sort of like stands off a little bit, we're going to get greater thermal strain. It's going to allow less heat loss and the soldiers are going to feel hotter. So these are the sorts of things we've always got to be weighing up of which way do we go. We can have that technology push, but we've also got to have the technology pull to make sure what we're going to use is actually going to be of some benefit. So hopefully tonight you've seen some of the complexity of the human platform and how we can manage to make the platform operate safely and how we can design for it. And what we look to do is continue to work with DiggerWorks and Army to continue to modify their body armour systems, other operational systems they use to maximise the protection and the performance of ADF members. Thank you.
Thanks very much, Mike. Now we have time for some questions. We are videoing both the presentation and the questions, and so if you ask a question, could you please speak up loudly so hopefully our microphone at the back there will pick that up. Please, questions.
Hi, thanks. Absolutely fabulous talk. I just want to take you back to two things you said. One was that those with high cardiovascular fitness are at higher risk as they push themselves. But then in the latter part, you were saying that it offers better protection, and that was in the trials. And I'm wondering what would underlie that. Is it like they push themselves, or if we've got sort of like a popping level, and they can actually tolerate closer to that, whereas those that peter out early?
Yeah, okay, so your question was, at one point I was saying that the cardiovascular fitness was a limiting thing, but then it was a beneficial thing. I suppose I didn't explain it well. It's a beneficial thing to prevent you from not dying. So you can't push yourself enough to get to those temperatures where you're going to melt your organs. Whereas it's a limiting factor from a capability perspective. So I'm not sure if is that sort of what you were asking or not?
Yes. Yeah, but again, it's in that sort of absolute upper thermal limit that we all have, and the capacity for those that have, because I mean, we're advising everybody, workers, the public, all manner of people, that better cardiovascular fitness is advantageous.
But then it's more
dangerous.
And that's where
get the message right.
And that's I think the thing is that the whole, there's two sides of it. Management needs to understand to manage those situations and not say, well, I can only do 30 minutes of work. Well, we're going to work for 4 hours, and know that we're going to get to an issue where we're going to probably have too high core temperatures. But it's also, I suppose, trying to educate the individual of those signs of when too much is too much. And that's what the ADF has a real problem with, is that the can-do attitude, and it's a very different environment to going to work, in a non-threat situation. So it's those people like ADF, or those people that are highly trained marathon runners. We see it in fun runs with, you need to have all the ice baths there ready for all the casualties coming in if it's going to be too hot, because those people have trained themselves enough, but probably not enough, and that they're the ones that are at greatest risk.
I'd like to draw the links between your study of females in combat capability and the heat stress. Your graphs, did that allow for any differences, or did it find differences between male and female, and how does that inform your calculations and your advice?
So the one where we've got all of the people all over no females in there. So that was done with an infantry battalion, and at the moment there's no females in those infantry battalions. But we know that there's all differences with females, with their body surface area, with their sweat rates, and all sorts of other things with hormonal cycles, with their core temperature fluctuating over the month and so on. I think that for females to, and with the physical employment standards, for females to serve in those roles and to be able to perform marches to those levels, they're going to have to not be in the middle of the female bell curve, they're going to have to be at the top end of the female bell curve. We haven't got into the detail of understanding the thermoregulatory systems of those people at that part of the bell curve compared to where the males are, but hopefully they're going to be starting to be somewhat a little bit more similar, I suppose.
And does it also impact on your body armour studies? Not from a shape point of view.
Yeah, so again, we haven't done female body armour studies and that whole thing of the surface area coverage. It's going to be an area that more nations are going to be getting more into, especially with the US looking at lifting combat trades for females. But what's combat these days? I mean, the logistics chain get hit, and there's females in the logistics chain, and they're wearing body armour. It's one thing that hasn't been addressed at this point in time. I think it's going to be like that bell-shaped curve. We're going to be split apart, but there is going to be some overlap, I suppose.
So your trainability capability for females is not yet taking into account these studies of your stress and your body armour.
Yeah, no, not exactly. But most of the time, when we've got to be actually doing the longer march in a cooler environment. So we're not really stressing people in those really hot temperatures in those activities.
This one at the back.
Mark, I know you've had some initial discussions with Navy for that maritime perspective of this. And I think one of the things in those discussions that I came away from was how much extrapolation or how much, we've got a table here that's good for Army, let's just use it. You know, your sense of the risk we might take in saying, we've got something, it looks good, let's just use it in other areas. It's that similar to the, do we apply it to females? How sensitive is the data and the results to changes in environment, circumstance or whatever from your perspective?
Yeah, so at the moment Defence has got the different work rest tables that are in policy that are the Army ones and the civilian ones. And the civilian ones are based on a 8-hour workday, 5 days a week, all sorts of different body shapes and sizes, ages, genders, everything else. So they're far more conservative because they're using a different model. They're not going as high. The Army ones are based on, assuming that someone's going to be able to do their 2.4K run and have a VO2 max of this and be acclimatised and so on. I would suggest that probably the people that are being, and this is not obviously working closely in the area, but the people in Navy or Air Force or wherever that are potentially doing some of those higher end jobs are probably going to have inherently the similar physical capabilities as the Army guys. It's not going to be across the board. I think it could be things like body weight and their 2.4K run. We could actually say these are the people that are going to be more at risk and these ones are probably not. So you could actually start to implement, say, the Army tables, but also have this other thing of who do we think is going to be actually at risk in that matrix of different body characteristics, fitness levels, age, experience, time in Darwin or whatever else. I think you've got to sort of like, and as you've been doing in Navy, it's a very hot environment in Northern Australia on patrol boats with lots of PPE on because that's what we need to wear. And so I think that the tables are probably a way to go to start with, but to be just looking at who may be at greatest risk. And we can provide, and there's lots of literature to understand who we can sort of like say, need to keep an eye on that one, need to keep an eye on that one, but let's still go with it.
Thank you.
Thank you very much for a very interesting talk. Clearly the objectives, from one perspective, the body temperature and dealing with the heat, with the armour to get the bullets out. What work has been done to try to use the armour or the clothing as a heat sink or that can help control temperature rather than, as you described it, the plastic bag?
Yeah, there's a number of different, well, probably over the last 20 or 30 years, people trying to work on cooling type systems, whether they be heat pipes or active systems where you're passing ice, cold water or whatever. The US Army have got a really interesting position, and they've had it for about 15 to 20 years, and it's more for the chem bio sorts of environments, but they've said you've got to be able to extract 150 watts for 4 hours and only weigh a kilo. No one's been able to crack that one yet. But there are people looking at more passive ways, and one of our groups is working with some people at CSIRO at the moment down in Melbourne, and we're just looking at it the other day, a heat pipe technique. And the main thing was that we could see that there was extracting a certain amount of watts from say, this little quadrant of our heated thermal sweating mannequin. But the key thing is it wasn't doing it all over the whole system. We said, well, if you can replicate that, 1, 2, 3, 4, and 4 on the back, the system's probably going to be okay. That's the challenge now, is to be able to do that. And that's just to get the heat extraction, but then what is the system that's going to go onto the side of it? And this is the thing with soldiers, even if it's going to be beneficial, it can't get in the way, it can't be extra weight, it's got to integrate with all the other things, and that's probably the greatest challenge. Is sometimes these things, the bulk of them and the weight of the exchanger is the thing that probably limits it for a dismounted soldier, and the duration it has to operate for. So I think in Afghanistan, guys were patrolling for 8 or so hours with body armour on. So it's got to be able to do that length, otherwise it just becomes another insulated bag. So I think there's a lot of people working in that area, but it's a real significant challenge. And one of the things we're looking at is that it may not have a massive effect on the core temperature, but if it actually can allow up here to be less stressed, because at the moment it's all the thermoreceptors saying you're hot, you're feeling terrible, and that's all getting fed back to the brain. So we haven't done the studies, and we've got some colleagues in Adelaide, but what we would really like to do is see what the actual operational effect is of how hot the person feels. So we know that they're not at a risk of heat stroke, but what's their operational capability like when they're feeling that hot? It's only we've only done half the problem. So cooling systems may not be the thing that's preventing heat stroke, but they may actually allow greater clarity in decision making.
Good question. The table, so they're looking at it's the maximum you can work.
Yeah.
But it's rare that a military operation will go for a day or something like that. You could be out there for weeks. Have you also looked at what's the recovery rate that when someone hits one of those limits, how long does it take them to get back down to the point where they can start to work back up again? Or
yeah. So there's work rest tables, which are 10 on, like 50 on, 10 off, and they're for a 5-hour work bout. I didn't put those ones up. I put up the continuous work table, which is you're going to do a bout and then you're going to stop. There's a recovery table that goes with it, and it will tell you how many minutes you've got to rest for. If you can get out of that hot environment, if you can take your body armour off, you don't have to rest for as long. So it's got all those factors in relation to what's the temperature and what can you take off. And what it says is that you should only do 2 cycles a day. So if you worked for 80 minutes and then you rest for 20, you can only do that twice. And we do know that core temperature will not return back to its normal level. Yeah, and it's going to take considerable time. So what we're going to do some research where we can, at the moment what we did when we're working with RAF was we said, based on the literature, we think you probably should reduce the subsequent work bouts by 1/3. And that was just based on our best evidence from the literature. It wasn't based on any controlled studies, but they needed something because they needed to be able to work. But what we're doing now is looking at doing a bit more research in that area to understand how much it does come back. And these are really hard studies to do because not it's hard to get the soldiers and subjects. It's hard to get the academics to want to do it because they're very prolonged studies. We usually do, 2 hours, but this is going to be a whole 8 to 10 hour day where you do you wait for it to rest, come back, then you go again, and you see, because what will happen will be like a sawtooth, so it'll be going up, but it will never be coming back down. And so we're trying to be able to provide guidance of how long you can work the third and fourth work back for.
Yeah, because I'm particularly thinking, my background is an engineering officer in the Navy, and I'm particularly thinking in that damage control situation where you're having to cycle fire parties through a very hot environment where they're fighting fire and shit, and where you've got a very fixed workforce and you can't do much. You can't bring in more people.
Yeah.
There's no one else there.
And probably one of the things would be to get them, and this is the other thing we'll probably look at as well, get them to aircon rooms, get them to active cooling systems so we can make sure that it's going to come back down. Get them to drink ice slushies.
Unfortunately, the first thing you do on a ship in a fire is you shut down all ventilation.
Thanks, Mark. Great presentation about the interaction of thermoregulation and the human body armor. And one thing you touched upon is, it is kind of like a sweat box. And obviously, in hot environments, your only way of cooling is evaporation. And with that suit on, you can't really evaporate. So you do sweat a lot and you get dehydrated. So has there been anything around kind of hydration protocols, hydration kind of regimens to limit that decrease in plasma volume and eventually, if you can stop sweating because you've lost too much weight? Increases the cardiovascular response.
So I didn't mention that, but on those work guidance tables, they have hydration rates as well. The interesting thing, as we know about hydration, is that the US used to actually have you had to drink 2 litres an hour in extreme circumstances, but we know the gut can't actually get rid of 2 litres an hour. It can only do about 1 litre to 1.5 litres. So they were just chugging heaps of water in. They end up killing, I think, 3 or 4 people from hyponatremia, from over drinking, because they diluted the blood, the sodium levels, to such a degree they died from over drinking. So they've really curtailed how much they drink. The maximum we're saying is that 1.5 litres. The real challenging thing for Army is that they've got to carry all their water with them. Our funny perspective on this is that we probably say that 2% dehydration is probably quite good for an infantry soldier because you're conserving. We did do one study with tank crews where we gave them a camelback with cold water, with 10 to 15 degree water, because 15 degree water you drink the most. Most people think probably 5 degree water is best, but it's about 15 because the thermoreceptors in your mouth, you'll stop drinking really shortly after you've got 5 degree water. If you've got 15 degree water, you'll actually drink more. But anyway, we had them drinking 15 degree water in a camelback, and we had another group drinking out of their jerrys that were 40 degrees. And the guys that were drinking the 15 degree water drank twice as much as the guys drinking 40 degree water. Great. But the guys that drank more water urinated half of the extra water out. So that's great for tank crews because they're carrying it around, but it starts to make you think if these guys have got to hump all of their load, their 40, 50 kilos, an extra couple of kilos of water that they're just going to urinate out. And it's this compromise of being totally dehydrated from that sporting perspective, absolute performance at Olympic Games, versus making sure guys aren't carrying too much and they're in this nice balance where they're conserving as much as possible. But the thing that here is it's around about 1.5 litres is the maximum. And the big one that came out of the heat injury policy sort of stuff was really that rehydration with meals and eating salty foods to stimulate thirst so that you're behaviourally drinking is probably the key thing that was a lot in policy of eat and drink as much as you can afterwards to try and rebalance and do it rather than forcing it. Like the American approach, forcing it and then killing people through overhydrating.
I think we'll have to call it a halt there because we're getting close to time. That's been a fascinating talk and a topic that I think is probably pretty new to most engineers, and it's certainly stimulated a lot of thoughts in my mind about the engineering challenges that arise from trying to accommodate these sort of different factors, and particularly the things like weight and the inputs and so on. So please accept a token of our appreciation here
Thanks a lot
for that, and please join with me in thanking Mark.